Should we wait or can we start? Should we wait for another couple of minutes so that others may join, or can we start the class? So for the exam, we are planning to have up to temperature measurement. Let's see how far we can cover until Friday. We have one more class apart from this. And if it is required, then Saturday, I may take one more class for the class that we missed on Monday, yesterday. So if it is okay for you, otherwise I will send an offline class if it's fine with you. It depends on what you want. And mostly the question paper will be problematic. Some sample questions we will try to send you. But meanwhile, you keep preparing the concepts very clearly, okay? And be ready for the exam. I think our exam is on Tuesday, right? Tuesday, 11 to 1. So please be prepared for the exam. Don't expect very theoretical questions and all. Mostly that will be in the form of questions. All the concepts will be converted in the form of questions and the problems, I mean to say. So that will be given to test your skills. All right. Let's wait for another couple of minutes and then we'll start. Okay, let's start the class today. So good morning, everyone. So today's class, we will continue from where we have left, that is temperature measurement. In the previous classes, we started with basic classification of different temperature measuring devices and what principles we are actually measuring the temperature. So we have clearly understood that temperature will be directly affected by some of these parameters, key parameters like pressure, volume, electrical resistance, expansion coefficients, etc. So temperature is not a direct measurement. We cannot measure it directly. So what we are trying to do is whatever the change that we are seeing in these variable parameters because of the change in temperature, we are trying to measure these parameters, and then from there we are trying to estimate what is the reason or what is the difference that caused this change in these variable parameters. That is the basic principle that we are following in the temperature measurement. Then we started with different kinds of temperature scales. We have understood how they are related to each other and what are the fundamental temperature sensing techniques that are in present we are using. So we have seen what is liquid and glass thermometers in the last class, and we will continue to see what are the other methods of temperature measurement. For the time being, we will start today the PV metal, the bimetallic strips, how it works and more. So we have started with this, the ideal gas thermometer. We have already studied in the previous class how, and now we will move on to the temperature measurement by mechanical effects. As I told you, mechanical effects means there is some kind of displacement, whether in the material or in the liquid that is inside the system. Okay, so based on the displacement that is caused in the material or in the fluid that is kept within the system, based on the change in their displacement, we will try to estimate the temperature. So that is basically what we call it as temperature measurement by mechanical effects. So as I told you, it uses the change in mechanical dimension with respect to temperature change. We have already seen it has liquid in glass thermometer, liquid in metal thermometer, and bimetallic strip. So these are the key examples of temperature measurement by mechanical effects. So let us start with, we have already started with it. So we have looked at liquid in gas thermometer. We have got a fair understanding of this as a household device to measure our body temperature. So we have looked at it. Okay, so what can be the what we need to do and all, we have already understood that. And so what are the fluids that will be used? What are the different key features in the liquid glass thermometers include? All that we have clearly looked at. And then we have also discussed about the response time, the sensitivity, what the different organic liquids that can be used and why they are restricted for high temperature measurement. All these key points we have discussed in the previous session. Let us move on. We will try to look at liquid in metal thermometers. So we have liquid in metal thermometers. The name itself suggests that it is liquid in thermometers instead of liquid metals. So the system, we will be filling it with liquid, and due to the changes in temperature of the liquid in the sensing bulb, it causes changes in pressure which are measured by a pressure gauge. It's simple that we have this kind of a liquid system over here. Okay, this is the bulb that we have had, and there is a bent tube. There is a tube which is bent in the form of a spiral, and the other end of it is connected to a pressure gauge. Okay, the other end of it is connected to a pressure gauge. And pressure and temperature, they are related by means of the ideal gas equation. So we will try to use that equation, making the other parameters as constant. All right. And when I keep this system, this measuring device in an environment where there is a change in temperature is happening, suppose there is a increase in the temperature. Because of the increase in the temperature, this fluid will elongate, or this fluid will displace within the liquid. And because of this temperature, this liquid will exert pressure in the pressure gauge. So there will be a change corresponding to the change in the temperature within the pressure. So based on the pressure change, we will try to estimate the temperature. So this is a simple fundamental principle that you know. So this is one of the thermometer with the liquid is kept as a in metal thermometers, where we are not directly measuring the temperature, but we are directly measuring the pressure, and then we are relating that pressure to the temperature. What is the temperature working range for this kind of an instrument is the temperature range is from minus 150 degrees to 330 degrees centigrade. This is the working range of this particular thermometer, metal thermometer with liquid as a working fluid, and they use propyl alcohol, methoxyol, xylol, mercury, etc. as the working substance or working fluid within the system. Okay, so this is the fundamental working principle. Now we will move on to some interesting thing which we call it as bimetallic strip. You might have heard about this bimetallic strip. When you are studying your mechanics of solids, you might have come across the thermal stresses. Okay, so whenever the body is subjected to some change in temperature, increase in temperature or decrease in temperature, depending on the property, what we call it as coefficient of thermal expansion or contraction, based on that, the liquid will either elongate or reduce in size. Okay, so when it is elongating in the longitudinal direction, in lateral direction, its size will decrease, or when it is contracting, its lateral directions will increase and longitudinally it will reduce. So that is basic property of any material, because it depends on the how good the expansion or contraction depends on the coefficient of the expansion or contraction. Based on that property, the materials will behave accordingly. All right. So, for example, you might have seen our doors and all will not fit properly in winter because they contract than the original size. That's the reason why we will not be able to push them freely as we will do in general in summer. In summer, they will elongate, so it's very free to move them. But when it comes to winter, they become stuck. They become tight. While closing the doors and all, you will observe that. So that is what will happen even for wood. So similarly, for metals also, this property is predominant, we can see in our metals. So what we are trying to do over here, so this kind of a measurement device, as I told you, measurement always is for different purposes, right? One is for understanding the actual value. The other one is we don't want the value, we want to control it. Okay, we generally want it to control certain temperature range within certain temperature ranges. So it can be used as a controlling device rather than as a measuring device. Okay, so this is the basic structure that we have given here, whatever in the system. So the name itself will suggest you that it is a bimetallic strip. That means there's are two strips. Bi means two metal strips. Two metal strips are bonded together as a single unit. Okay, so they are made of two different materials. Okay, they are not of the same materials. They are made of two different materials. And when they are heated up, when they are given heating temperature, what happens is initially they are straight and of initial length, same length. But what happens when I give temperature to this, depending on their coefficient of expansion and contraction, they will either elongate or contract. So since they are not of uniform alpha or uniform coefficient of expansion, they will elongate or contract in a different way. That means this may elongate more and this may elongate less, creating temperature stresses within the materials. Since they are bonded, even though this material wants to move or elongate freely, the bottom one, which is not having coefficient of expansion as much as the top layer, will, since it is getting bonded, it restricts the expansion of the top metal. So thereby what happens, the thermal stresses will induce within the material, and the material, instead of taking a straight length, it becomes a curved shape. It takes a curved shape like this, either convex or concave depending on expansion or contraction. So now, as I told you, this can be used mostly as a controlling device rather than a measuring device. Suppose if we want to have a control, that means for a particular temperature range they have to be in contact, and when the temperature range is not reached, it is lesser than the required temperature, then it should be out of the connection. So you can see over here, when it bends in with a curvature like convex shape, what happens, this will move up, this particular contacts will move up. Okay, this will take a shape of a bended one like this. Okay, so when it takes a shape like this, what happens, this one will come in contact with this. This happens when this reaches a particular range of temperature. So this is connected to a system where we want to control the temperature. So this will be connected to that system. Because of this, the temperature will reach this body, and there is a change in the dimension of the body, geometrical shape of the body. Because of that, there is a contact or discontact misconnection happening at the other junction. So when this is in connection, something will flow, and if it is not in connection, there will not be any flow. So this works as a controlling device rather than as a measuring device. Okay, by bonding two different metals together, you can make a simple electrical controller that can withstand very high pressures. It seems like someone has asked a question. Is it correct? Anyone? Is there any question there? Correct. MCBC tend to use a bimetallic strip, and even in the solenoid valves, we call it solenoid valves. Now they are being used in, they're kind of used in mostly in the what we call freezers and all, refrigerators and all. So, but you think of it, even general thing I told you, suppose if you are looking at a battery cooling thing, suppose for example, I'm telling you, the best thing is the battery performance will become better when the temperature rises from 15 to 40 degrees centigrade. But when it goes to lesser than that, the battery performance becomes lower. Correct. So what we can do is by using these kind of things within the foreign countries and all, where the temperatures goes beyond or lower than the 0 degrees centigrade, there we can use this as a controlling device to keep the battery working temperature within the particular range. I'm just telling you for as an example. So this is a good idea to keep. Okay, so bulb thermometers are good for measuring temperature accurately, but they cannot be used to control the temperature. Using them for controlling the temperature is difficult with thermometers. But since they are made of metal, bimetallic thermometers are good at controlling things. So the contact and non-contact can be made very accurately or precisely with the help of a bimetallic strips. Okay, so what is the radius of curvature? The question is, how do we estimate the radius of curvature that can be coming out of two metals which are bonded together, which are having two different coefficient of expansion? How do you estimate the radius of curvature? How much it can be? So Eskin and Fritz, they have done some extensive calculations or experiments on this, and they have given a basic equation for metallic strips based on which the radius of curvature R is given by T, the thickness of the materials, 1 plus m. I will tell you what is m, and then 1 plus mn into m square plus 1 by mn. Alpha 2 is the thermal coefficient, alpha 1 is also thermal coefficient of material 1, alpha 2 is the thermal coefficient of material 2, T is the ambient temperature, T0 is the surface temperature. Based on that, we will be able to find out what is the exact radius of curvature that will come in the bimetallic strips. So I forgot to give you this equation, what we call the, what is m and n, I haven't mentioned over here. So I will try to give you that, okay, in the material. So what do you mean by m and what do you mean by n? These are the two things that we have to give. I think I have not updated this. I will try to do this when I share the material with you. Okay. For the time being, alpha 2 and alpha 1 are the coefficient of expansion. T is the different temperatures, which is at initially and finally. And what is m? M and n we need to find it. That is what I will disclose that and when I share this material. All right, so any doubts in this up to this? So the bimetallic strips, as I told you, they work at best at higher temperatures because their accuracy and sensitivity, they generally tends to reduce at low temperatures. They are very good at very high temperatures, but not as accurate and precise or sensitive at lower temperatures. Therefore, the kind of designs that we use have to be changed. For it cannot be every time a flat plate kind of a thing. So for different applications, we may have to vary that. So if you want to measure it, basically, how do we do that? If you want to control it, this kind of a design can help. But if you want to use it as a measuring thing, how do we do that? So one of the most popular design that we have is the flat spiral, as it's shown in here. So the bimetallic strip is wound like a spiral thing. Okay, and at the center, the pointer is connected to this. And based on the temperature, this connection, this viral spring will be unwound or it elongates. Based on that, the pointer will move on a graduated scale. Okay, so there are different kinds. Now, a flat spiral we have a single helix or multiple helix. Depending on the application, we can have different kind of things. For those who has interest and all, you can go through it. What is a single helix and what is a multiple helix form, and etc. So as I told you, they can be customized to work as a recording thermometers. Okay, so how do we record it? So one thing is we are able to measure. The other thing is we are able to control it. Two things are done. Suppose, what if I want to record the readings? How can I do that? So that can also be done by customizing it, by having a pen kind of a thing to the pointer. Suppose if you have a pointer kind of a thing, and the pen is located in such a way that it makes recordings on a circling chart. So if there is a chart on which you can rotate this pen, so this pen will record whatever the changes that are happening on the winding, that is the flat spiral winding, that is, and this based on the pen movement or the pen markings on the paper spiral or circling chart, we can always find out what is the, we can always record what is the changes in temperatures that has happened. Okay, that is one way of looking at it. But now we have got more digital devices and the pen and all. These are used primarily in the previous, like seismic thermometers kind of thing, where earthquake happens, the pen will record the oscillations, right? So that is that is one of the examples still we are using, but now we have many digital devices where we can record that. And the bimetallic strips generally comes in very long sizes, as they are coiled into spirals which make them compact and small in size. Generally they can be very long. And what will happen is, because of this coiling and compacting, making into compact, it increases the sensitivity of the bimetallic strips towards little temperature. We can always alter the sensitivity by means of compacting them, taking a long bimetallic strips and then winding them into a very compact or small spiral windings, and then that can be used for increased sensitivity of the strips and then for little temperature variations also. They can be scaled up or down, so they can be increased in scale, size, or reduced in scale. But in primarily, the primary purpose of this is to control mechanical control or other purposes. Okay, so in a smaller scale. On a larger scale means most of the things that we do with the bimetallic strip is controlling mechanical. It will be used as a mechanically controlling device. As temperature is a process parameter. What do you mean by a process parameter? A parameter which actually governs the process. Okay, so this temperature, generally in many industries you can see that there is a temperature range in which the process has to happen. Beyond or less than that, beyond that range we cannot use that system. So naturally what happens is, this will not allow us, these bimetallic thermometers will allow us to maintain that range of temperature rather than measuring the temperature. Once it goes beyond it, the switch will be off and the process will stop. So that's how these metallic strips will work. So majorly that metallic strips we will use for this purpose. On a smaller scale, it can provide the force and movement for micro machine integrated circuits. You can see that the name itself, MMIS. What do you mean by it? So there is a micro machine integrated circuits. There are very small, micro means 10 -6 meters, and so such kind of machines, that means very small movement is required. So what happens is the curvatures that is happening on this things will move the pointer or the circuit, so that we can be using them in the micro machine integrated circuits. Very small movement can be possible by using these bimetallic strips. So one is controlling as a mechanical control switch. Other one is it can be acting as a driving force. It can be used as a driving thing for the micro machine integrated circuits. Okay. So up to this, we have finished the temperature measurement by mechanical effects. Any questions in this? I'll be happy to take. Okay. If not, we will move on to the temperature measurement by thermoelectric effects. Okay. So what do you mean by thermoelectric effect? Temperature and electrical effect together. We have mentioned over here, thermo, that is heat, and electrical energy, they are combined together. So what is the thermoelectric effect is? It is nothing but the direct conversion of temperature difference to electrical voltage. Whatever the change in temperature that is happening, we try to convert that into electric voltage. That means there is a direct correlation between the temperature difference and the electrical voltage, or vice versa. That means whenever there is a change in electrical voltage happen, temperature do change in the materials. Okay, so a thermoelectric device, what it does, a thermoelectric device, it creates voltage difference when there is a temperature, different temperature on each side. When you have two different temperatures, it creates a voltage potential. Or when a voltage is applied to it, there is a temperature difference that will be created to the two ends of the materials. Okay, so this effect we will use to generate electricity and we use to measure temperature or change in the temperature of the object. Okay, again, because the direction of heating and cooling is generally determined by the polarity, on what polarity you are connecting the applied voltage. So based on that, we can use these thermoelectric devices sometimes as temperature controllers also, based on applied or polarity, application of polarity of the applied voltage. The first one is, we know that there are three kinds of effects. One is the Seebeck effect, Peltier effect, and Thomson effect. You might have studied this in your +2. So the first one, the most important thing is the Seebeck effect. Peltier is also important nowadays from the research point of view. I will tell you what it is if time permits. What do you mean by Seebeck effect? Seebeck effect, Seebeck is a scientist who first found out this effect. So on his name, this effect has come into existence. So Seebeck effect is a phenomena in which a temperature difference between junctions of two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. So we have two different materials, two distinct and different materials. Suppose this is one material, okay, and this is another material. This is copper and this is metal. Sorry, this is metal A, this one is metal A, this one. Two dissimilar metals. This is metal B, this is metal A. Two dissimilar metals are joined together. They are forming two junctions, one at here, one at here. Ideally, these two are different, but only at two ends we are connecting them, forming a single end. And one is maintained at a different, the two junctions are maintained at two different temperatures. Suppose this is maintained as a hot junction. That means here it is, temperature is different, whereas this temperature is different. So one is maintained at a cold junction, one is maintained at a hot junction. It is relative term. So it's basically a relative term. What do you mean by hot junction and what do you mean by a cold junction? If one end is maintained at a temperature higher than the other, so naturally whichever is having higher temperature, we call it as a hot junction. The other one becomes a cold. So when these two things are created, two dissimilar metals are created, are generated or produced by entwining them at two different ends, okay, if we are maintaining them at two different temperatures, because of this temperature difference, some voltage will be induced. Okay, so now what we are trying to do is, I am actually connecting this to a copper wire with a voltmeter. So this end is also connected to a copper wire with a voltmeter. You can see that here the copper wire is connected to the same material of metal A. Only metal B is different, which is connected at two different junctions, and the temperature at the two junctions are different. Because of this temperature difference, we have an EMF or voltage which is produced. So what is that voltage that is produced? We can write it down in the form of a tabulated curve. So when this one is kept at 0 degrees centigrade, 10 degrees I have seen 5 volts. Then I increase this to 20 degrees, then I have seen 10 volts. When I increase to 30 degrees, I am seeing 15 volts. Likewise, I have a calibration curve based on which these are all intermittent kind of values, right? For intermittent values, I found out what is the voltage, and now whatever the temperature difference, that whatever the voltage that we get, that is measured by the voltmeter, when one of the end is connected to an unknown source, whenever I don't know the source temperature, I keep that source temperature here. This is kept at a known temperature of 0 degrees centigrade. This temperature I don't know, and then the corresponding voltage will be generated. From the calibration curve, I try to find out what is the temperature difference, delta T. So I know what is 0 degree, what is the cold bath temperature, TH minus TC. Delta T I found out, TH minus TC I found out from the voltage. From the intermittent values, I try to find out a calibrated curve which gives the continuous values of any voltage to delta T relation. So from this, I will find out what is delta T, and since I know the cold temperature, I will be able to find out the hot junction temperature. Am I clear? So this is what we will do in general with Seebeck effect. Basically, using a Seebeck effect, we are trying to find out the temperature like this. So this is basically your thermocouple. Okay, this is basically your thermocouple. So thermocouples are generally two different materials are joined together, and at one end we are actually connecting them. The other ends we are connecting to the terminal of the data acquisition system. Whatever the data acquisition system that we have, for example, we call it as a data logger. So one end is connected to a positive and another one is connected to a negative thing, and then the device will automatically detect because there is a function already written in that. Based on the calibration that we have created, it will be able to find out the exact temperature. In terms of direct temperature, you can see in the data acquisition system or data log. Clear? So the device which works on the based on one of the thermoelectric effects is what we call it as a thermocouple. And the thermocouple is a device, a very important device, because in academia and in industry, if you want to measure the temperatures, this is the first and foremost thing we try to devise for measuring the temperature. All right. A thermocouple is a device consisting of two dissimilar conductors or semiconductors that contact each other at one or more. As I told you, so there are two different materials. One is connected at one point, another one is connected at another point, and they are making two different junctions. Okay. So a thermocouple produces a voltage when the temperature of one of the contact point differs from the temperature of another in a process known as the thermometer. As I told you, so when one known temperature, one junction is kept at a very known or controlled temperature, whereas the other temperature is kept at an unknown temperature. So thereby, using some voltage and measuring that voltage, we will be trying to relate that difference in the voltage to the difference in the temperature. The same thing mentioned over here, that it creates EMF when there is a temperature gradient, and this EMF is used to develop an open circuit voltage. Under open circuit condition, when there is no internal circuit flow, the gradient voltage is directly proportional to the temperature gradient. So delta V is directly proportional to delta T. And again, there is a proportionality constant, what we call is S of T, which is nothing but the Seebeck coefficient. Seebeck coefficient is a strong function of temperature. So it depends on the material property. So based on the temperature dependent material property, the Seebeck coefficient will be there. So delta V is equivalent to some proportionality constant, which we call it as Seebeck coefficient, into delta T. So that means the difference in the temperature. So that is the relation between these two. So now we have many types of thermocouples depending on what are the materials that you are using as a thermocouple materials. Okay, so we have T, J, K, and E. So these are the general types of thermocouples that we use in our academia as well as industry or in the research mostly. So what do you mean by a T-type thermocouple? These are very important, not for the examination point of view. Having this knowledge is very important. What is a T-type thermocouple? T-type thermocouple, it consists of two different materials. One metal is copper metal and another negative metal, we call it as constantan. Okay, copper and constantan, they both are entwined together to form two different junctions. Then we call it as a T-type thermocouple. This is very important for exam point of view also. So what is the temperature range that we can find? We can see there is a very low temperature that we can find out. Minus 200 to 350 degrees centigrade. It's not very high. So 350 plus 200, 550 degrees range we can use to measure the degree centigrade. We can measure by using a T-type thermocouple. Each one is having their own advantages and disadvantages depending on our requirement we use. The next one is a J-type thermocouple, where you are using iron as the positive metal or alloy, constantan as a negative metal or alloy, and we can measure this from 0 degrees to 750. Below temperatures we cannot measure. From 0 to absolute 0 to 750 degrees centigrade we can measure from this. It's not absolute. 0 degrees centigrade to 750 degrees centigrade. Absolute means 0 Kelvin, right? So it is 0 to 750 degrees centigrade we can measure with the help of J-type thermocouple. Similarly, we also have K-type thermocouple, which is one of the most highest range that we have is this K-type thermocouple, But as I told you, if the range increases, what reduces? If the range of the instrument is wide, what is that will reduce? What is a property, or what property will reduce? Simple example, if the number of class strength is lower, the teacher may be able to distinguish each person. What happens if the class number is more? Compare 20 people to, suppose say that 200 people are there. What happens? The teacher may not recognize each and every.
Sensitivity will decrease.
That is what will happen. So when the range increases, the sensitivity will automatically will reduce. That is one of the problem. So depending on what is your application, you have to pick out which thermocouple you have to use. Again, there are other problems which we will discuss in the coming slides. So those also have to be taken into account. But this is based on the range. If you want to consider the thermocouples or classify the thermocouples, this is the major tabular column that will help you. Okay, the K type will have chromel and alumel. Okay, these are the two metals that we use together to form this. Look at the temperature range. It is from minus 200 to 1250 degrees centigrade. The highest range we can get. Up to 1250 we can use by having a K type thermocouple. And the last one, we also have other I type and all, but I am giving you the most important thing here, only here. So that is basically your E type thermocouples, which is having chromel and constantan. Chromel and constantan is being used, whereas its range is minus 200 to 900 degrees centigrade. Okay, so this is also used for, it is also used as for many applications. So mostly you can see constantan is used as the negative metal, except in the K type, and copper, iron, chromel as being changed. Positive metals are being changed. Because of these, the range of the temperatures that we are measuring is getting changed. Let us move ahead and discuss what are the advantages of thermocouples. So most practical applications, generally the temperature measurement ranges from cryogenics to jet engine exhaust. The highest temperature we generally tend to have, when we tend to get, is in a jet engine exhaust. A couple of thousands it will be. And from cryogenics, which are negative temperatures, we can find out in cryogenics. Okay, so up to that ranges, the maximum ranges of this cryogenics to jet engine exhaust, we can measure by using thermocouples. So what kind of thermomaterials or metal wires we are using, it can measure up to minus 200 to 2500 degrees centigrade. In the earlier case, E type we have, K type we have shown minus 250 to 1500 degrees centigrade, but by using different alloys, we can go up to 2500 degrees centigrade. Okay, so that is the first advantage of a thermocouple. That is, it has wide variety of temperature ranges that can be measured with the help of a thermocouple. Second thing is they're robust in nature. That means they're very sturdy. Okay, they're rugged devices. They are not affected too much by shock and vibration. And even in the hazardous environments, by picking up suitable materials, we can use even in the hazardous environments like combustion chambers and all. Okay, they are able to withstand those temperatures. They have that properties like it can withstand a huge temperature. They don't melt away because they have higher melting point temperatures. So based on that, we can decide that they are robust in nature. The important another advantage is rapid response, because they are very small and they have very low thermal capacity. The storing capacity if of a thermocouple is pretty low, and its thermal conductivities are generally high. So because of that, what happens is the thermocouples responds very rapidly to temperature changes, suppose especially when the sensing junction is exposed. Okay, sometimes even they can respond to a few hundred milliseconds temperature variations also. Okay, and another important point that we can measure, that we can take care of, is no self-heating. Okay, they don't need any excitation power. That doesn't require, generally, if it requires a minimum energy to start, like in thermometer, where the mercury has to take the temperature, minimum energy to self-excite it. After that only it will be able to show the displacement in the liquid, right? So, but when it comes to thermocouples, we don't need any excitation power. So it immediately starts. Okay, so therefore, whatever the temperature that it takes, it immediately transfers because it has low thermal capacity. It will not store the energy. So therefore, the response is good. Immediately, it tends to respond. Another thing is, it don't get heated up. Sometimes if it gets heated up, for example, after a prolonged usage, it may get melted because the temperature kept on raising. So that doesn't happen with the thermocouples. Okay, they are not prone to self-heating and they are pretty safe. They are intrinsically safe because there is no increase in the temperature. So for longer periods, we can use for a particular application without any hazardous effects on the person who is taking care of the measurement. What are the disadvantages? So when it has any human or any device, it also have some advantage, some disadvantage also will have. So complex signal conditioning. What do you mean by complex signal conditioning? So you have got the voltage signal which is having a lot of noise. Okay, a lot of noise will be there. So therefore, for getting that means you. I hope you know what is signal noise in. So what I want to say is, I am expecting a curve like this, the variation in the voltage like this, for example. But in actually what happens is, it will happen like this. A lot of variations will happen. So out of these variations, I have to get a very smooth curve that predicts the behavior of this material. So this is what we call it as signal condition. Okay, so substantial signal. So that means whatever the variation that I'm seeing over here, I should always try to take the mean value of this by different methods, and the different values that I'm getting, the different data that I'm getting, I'm not taking all the data into account except that the mean or the central tendency of the discrete data that I got. I want to take that data into my effort. Okay, so that is what I am more concentrated into. So what I require with the thermocouples is, thermocouples generally tend to give a lot of discrete data. That means the data will have a lot of noise. So it's imperative that we need to have a very good signal conditioning to get the temperature readings. So when you have a data logger, you should have a very good signal conditioning system. So there is this system should have algorithms which takes out the noise very effectively. So that is what I'm calling it as signal conditioning. But signal conditioning, it generally requires large investment in design time. So to avoid errors that actually degrades the accuracy. So signal conditioning again is we have to invest some cost and design to actually reduce the errors. So therefore, it is cumbersome. So that there is some kind of difficulty in having a good signal conditioning system. That is one of the disadvantage of a measurement with thermoelectric. Don't worry, now we have good signal conditioning system, so it is not a big disadvantage. When it comes to accuracy, in addition to the inherent accuracies in thermocouple due to metallurgical properties, it is only accurate traditionally within 1 degree centigrade and 2 degrees centigrade. When it comes to accuracy, plus or minus, what is a deviation? So that deviation we are having high. You can measure the temperatures at the lowest, the variation will be plus or minus 1 degree centigrade. Very now sophisticated thermocouples have come which can measure up to plus or minus 0.5 degrees centigrade and all. But in general, you cannot have 0.001 degree centigrade deviation and all. So that much accuracy we haven't got with thermocouples. So it is generally having this K-type, J-type thermocouples. They are generally having the deviation to be 1 degree to 2 degrees. Apart from the other things, we also have a bigger problem with thermocouples is they are more susceptible to corrosion. Okay, so since they are two dissimilar metals and they are used in different environments, they are over a period of time they are exposed to the environment where it may lead to corrosion. They may get oxidized depending on the material. They react with oxygen in the air and they get corroded. They form a layer over it, and therefore it tends to deteriorate over the years. Okay, so they are generally needs protection, special care and maintenance. from the dust and from the oxidation. So that is one of the biggest problem with this kind of thermocouples. Okay, so especially E-type thermocouples, generally they are more susceptible to the corrosion. So if you are using in a humid conditions, if you are measuring in a humid condition, you generally tend to see whatever the thermocouples which doesn't react with oxygen much, which doesn't react with humidity much. So therefore, that is what we will be looking at. So that is one of the problem with the corrosion. You cannot continuously use without any protection in the, so over a period of time it tends to have the accuracy is lower. So always whenever you want to use the thermocouples, do remember, not only for thermocouples, for any instrument, if you are a good experimenter, the first thing you have to do is properly validate, properly calibrate the system. You have to calibrate before taking any measurement, Okay, so that is the prime important fundamental aspect that you should learn as a student, that before using any instrument, you should ask the person, what is the calibrations, where is the calibration certificate? You tell me for what value, how much error that I can get. All right, so these materials may have one kind of calibration for the initial year, for the second year, it may vary. So you have to keep on calibrating it so that your errors will be lowered or you can negate the errors. As I told you, since you are using microvolt level signal changes, noise will be too much, and sometimes the electrical field and magnetic field, they will affect the signals. So therefore you will have a lot of noise when you are using thermocouples. So appropriately you have to make sure that we are taking the measurements without in an environment where we don't have magnetic or electrical fields interfering into the measurement process. Okay, so next we will move on to the temperature measurement by thermoelectric effect. So up to this, any questions, guys? Please ask me.
Yes.
So should I stop at here? I think it should be more than sufficient for today. Should I continue? We have few laws which electric effects and all. Okay, we will stop at this point of time. Only 5 minutes left over, so we will stop at this point. So tomorrow, do we have a chance of any extra class? If anyone, any faculty is not willing to take, please inform me so that I can take that particular class. 1 second, I will answer these questions. Let me stop the recording first. Yes. So let me understand. Amarnath, so can we use nitinol wire for such measurements? So why nitinol wire? Specifically, Amarnath, I have not come across this nitinol wire. That's why I'm asking. Why you are specifying nitinol wire? See, you look at this in a very fundamental way. In a very fundamental way is, those two dissimilar metals which we are bonding together, they should not react with each other because of the bonding. And whatever the properties that they have, because of the temperature difference, it should create an EMF which is easy to measure. The EMF that is created should be easy to measure. So that is a simple logic that we can have. Okay, so any two materials of different properties which can produce this can be used. I am not able to answer that specific question like nitinol wire. What is the speciality of that wire? Second one is, if Seebeck coefficient is temperature different, then how temperature memory materials? Okay. Yeah, you can, probably you can try it, but these are the standard thermocouples that we generally use. What is the advantage of temperature memory materials? As far as I understood from the temperature memory, because of temperature, if there is a deviation within the material, it tends to, when you take out the temperature to the initial temperature, it comes back to its original shape. So that is what you are saying as a memory material, isn't it? So what is the advantage of it? Whether it comes back to original shape or not, that can be used as a, that you can use in the form of a bimetallic strip or something. You can develop a controlling switch kind of a thing with that. But I don't think anything to do with the Seebeck effect. In the Seebeck effect, there is absolutely nothing that depends on the material change or the mechanical change. Okay, it's just the temperature difference that creates voltage. Okay, it's basically the electrons flying over because of the variation in the temperature. So how does this will fit into that particular principle? You should think. Are you clear, Amarnath? So it depends on where. As you said, according to what you said, the Nitinol wire we can use as a mechanical switch, where within a temperature it bends to a particular shape, and then it creates a point of contact. And when the temperature is lowered, it comes back to its original shape. Therefore, it cannot be any contact. That means switch is off. So that kind of a thing you can do it. That you can try it. It's a good study that you can do. Coming to Amarnath Biswal, another question. If Seebeck coefficient is temperature dependent, then how can it interfere our temperature measurements? Why? See, it's like a proportional constant you are getting. Whatever you are getting a curve like this. So the Seebeck coefficient is basically like a property, right? Okay, thermal conductivity, if you take, is thermal conductivity a property of the material or not? It's based on temperature. Based on your temperature change, your thermal conductivity of the material will change. But when it comes to Q, heat transfer, Q is equivalent to K dt by Tx. So it acts as a function, right? So for different materials, it is not in the same proportion, but it varies. How it varies is dependent on the Seebeck coefficient. For a particular temperature difference of 30 degrees, if suppose K-type thermocouples is producing 10 volts of current. For the same thing, if J-type you are taking, it may not produce 10 volts. What is the thing that is creating the difference? That is nothing but your Seebeck coefficient. Okay, so whenever you are doing a comparative, or whenever you are doing a calibrate, and you have this calibration curve, and you try to make an equation of that, or this a linear equation if you form out of it, whatever the slope that you are getting, kind of, so that is basically your coefficient that you are trying to use. So that is what actually tells you. Any other questions? I hope the topics are clear. Anything further is required? Jayesh, is it okay?
Yes, sir. It was clear. Yes, sir. Yes, sir. Definitely.
So, if tomorrow's any vacancy is there in any one of the class?
Okay, sir. I will talk to CR and let you know, sir, if there is.
If there is anything, you just let me know, because tomorrow I have some free time.
Okay, sir. If there is no vacancy, we can have a synchronous class, or you can send a recording or something.
That is okay, but most of you students likes to have this class, and
yes,
as I heard,
synchronous class.
Yeah, sir. if not tomorrow, at least in Saturday we can have 1 hour class, so that we'll finish the temperature thing up to temperature. Okay, so make sure that you are ready for the up to temperature measurement.
Yes, sir. Okay, sir. Definitely.
Right. Any questions, Karthik? Abhilash?
Yes, sir.
Okay. Okay, then if you have no questions, then I'll try to wind up the session for today. Okay, and I'll try to update the links to you in LMS for the recordings. I forgot the previous recording also. I will put that today. Okay, please take care, and all of you stay safe. Thanks for attending the class. Bye.